Hello and welcome to today's lecture. So, in the last class we had briefly touched upon the idea of central limit theorem, right, one of the most important theories in the field of statistics. Okay. So, before going to the central limit theorem, I will begin by discussing about again sampling distribution, right. So, what is the sampling distribution, and you can find the sampling distribution, okay, of a statistic. Okay. So, by this I mean you can compute the sampling distribution of a mean, of a median, or any other measure that you define. Okay. So, what is the sampling distribution of the statistics? So, a sampling distribution of the statistic is the probability distribution that you obtain. So, probability distribution of the statistic that you obtain by repeating or repeatedly drawing a sample. Okay. So, in other words, imagine you have a population of n numbers, let us say n numbers, okay, and from this you draw a sample of n numbers. Okay. So, based on this, for example, if my 5 numbers are 1, 2, 3, 4, 5, okay, and let us say my n is equal to 3, right. So, in how many ways can I draw 3 numbers from n? So, it can be n c n, okay, the different ways in which I can draw 3 numbers from 5, right. So, this is 5 c 3 equal to factorial 5 by factorial 3 factorial 2 is equal to 10. Okay. So, there are 10 ways of drawing a sample of 3, and one example is 1 2 3 or 1 2 4, so on and so forth, right. So, from these you can, let us say, compute the sum of these numbers. In that case, this will be 6, this will be 7, and so on and so forth. Okay. So, you can ask the question, what is the probability distribution of the sum that you obtain? Okay, and this is the sampling distribution. So, ideally the concept of sampling distribution is very important, because you do not know that you want to find out some information about the population based on the sample that you draw. So, central limit theorem is that theorem which allows us to correlate the sample mean or median or any other metric with the population metric. Okay. So, what does central limit theorem state? So, I had discussed this brief example in last class, right, where if you draw a, so if you are interested in rolling a die, okay, rolling a die, okay, and checking out its value that you get, right. So, the distribution, okay, the distribution will be fully flat. So, each of these values, okay, is 1 2 3 4 5 or 6, okay, this distribution is flat. But if you roll 2 dice together, okay, and you compute the average score that you get, so you will begin to see that slowly your distribution will look closer and closer like a normal distribution, okay, and with increase in the averaging process. Okay, and this is what central limit theorem says. So, what does the central limit theorem state? Okay. So, your central limit theorem states that if x1, x2, xn are identically distributed, independent random variables with mean mu and variance sigma square, okay, then summation of xi, that is x1 plus x2 plus x n. So, this is also a random variable, will also follow. So, we will follow a normal distribution with mean n times mu and variance n sigma square. Okay. So, this is your variance, okay. And this is very easy to prove. Okay. This is very easy to prove. So, I can write x as x 1 plus x 2 plus x n. Okay. So, since each of these variables are independent, the expectation of x is e of x 1 plus x 2 x n. Because each of these random variables are independent, we can break it down into e of x 1 plus e of x 2, so on and so forth, plus e of x n. So, this is going to be n. So, mu plus mu plus mu. So, this is n times. So, that is why this will give you the expectation of this x is simply equal to n mu. Okay. And by the same token, I can write variance of x is equal to summation of variance of x I by, again, because these random variables are independent, and so I will get n times sigma square. Okay. So, this variance is n times sigma square. Okay. So, what in other words, which would mean that if you have, so I can say that summation x I is normally distributed with mean n mu and variance n sigma square. So, then I can say that sigma x I minus n mu by sigma root of n. So, this is nothing but sigma root of n whole square, right. So, this is approximately equal to a standard normal variable. Okay. So, in other words, probability of summation x I, let us say less than x, you can approximate is the probability of summation x I minus n mu by sigma root n less than x. Okay. This is the approximation. So, let us first try out few examples how this theory can be used. Okay. Imagine you have an insurance company, okay, which has 25,000 policy holders. Okay. So, the yearly claim of a policy holder is a random variable with a mean of 320, right, and standard deviation of 540. Okay. So, this is the background information. So, we want to compute the chance that the total claim, okay, disbursed by the company is greater than 8.3 million dollars. Okay. So, this is what we want to compute, the chance that the total claim is greater than 8.3 billion dollars. Okay. So, if we are to make use of the central limit theorem, so what we are given is, so So, xi is the random variable of claim of ith individual. Okay. So, we want to, so the total claim disbursed by the company is going to be summation of xi. Okay. So, each xi has a mean equal to 320 and sigma equal to $540. Okay. So, my summation xi must follow a normal distribution. So, this is by central limit theorem. Okay. What I can say is summation xi follows a normal distribution, okay, with mean equal to 320 into the total number of policy holders. So, for each xi you have mean as 320. So, for summation xi the mean has to be 320 into 25,000. Okay. So, if you plug in the numbers, this will come to be 8 million. Okay. And standard deviation, so this will be equal to, I can say sigma star equal to sigma into root of n. Okay. So, which is 540 into root of 25,000. Okay. So, this will approximately come to be 8.5 into 10 to the power 4. Okay. So, we are asked to calculate probability that summation xi will be greater than 8.3 million. Okay. So, we can approximate this as the probability summation xi, okay, minus n mu by sigma root n, okay, is greater than, okay, 8.3 into 10 to the power 6 per million minus, so n mu is going to be 8 into 10 to the power 6 that we found, and sigma root n is going to be 8.5 into 10 to the power 4. Okay. So, this is equal to probability of, so this is your standard normal variable now. So, this is z greater than, so if you plug in the values, this will give you a value of 3.5, and this comes to approximately 0.00023. Okay. So, as you can see that where there is very little chance that the claim is going to be more than 8.5 million. Okay. So, this is how you make use of central limit theorem to gain an idea of, or to make a prediction of calculating the chance that this particular insurance company will have to disburse these funds. And these are calculations which the company does at its end to figure out how much the insurance amount it should charge, so that it makes a certain amount of profit. Okay. So, let us go to another example. Okay. So, think of a bridge. Okay. So, bridge, each bridge has a certain capacity of how much weight it can bear. Okay. So, imagine for a given bridge, so the weight it can bear, okay, the weight it can withstand without any damage. Is a random variable with mean of, okay, with mean of 400 tons and sigma equal to 40 tons. Okay. So, cars ply on the bridge on an average. Okay. So, the car weight, imagine it is a random variable with mean, okay, with mean 3, okay, and okay, and with standard deviation to 0.3. So, the question is how many cars how many cars would have to be on the bridge for probability of damage equal to 0.1. Okay. So, what this question tries to understand is how many cars is the can the bridge bear. So, there is damage of 0.1. Okay. So, how do we go about this problem? Okay. So, what you have to calculate, what you have been asked to calculate is, so let us say xi is weight of ith car. Okay. So, if there are n cars on the bridge, okay, so the load on the bridge is equal to, okay, so since x, okay, so the load on the bridge is equal to summation of xi, right. So, what can I say about summation of xi? So, each of these xi's is a random variable, okay, with mu is equal to 3 and sigma is equal to 0.3. Okay. So, I can say summation sigma xi is a random variable with mean, okay, 3 times n. If you have n cars, 3 is the mean for each car. So, mean will be 3n and standard deviation will be 0.3 into root n, okay, 0.3 into root n. Okay. So, when I want to calculate the damage on the car, so from the damage on the car, we are thinking of a situation that 3n, which is the total load on the car, this is greater than 400, right. 400 is the weight which can be withstood by the bridge. Okay. So, summation xi minus w, okay. So, this is the effective weight mismatch between the weight of the cars on the bridge and the weight that can be withstood, is a random variable, okay, with mean, this has a mean of 3n minus 400, okay, and a standard deviation. Okay. So, how do we calculate the standard deviation here? You have 2 random variables. So, you define a random variable, let us say y, as summation of xi minus w. Okay. Mean is this, okay, and you know, so since these two are independent of each other, so your variance of y, okay, will be variance of summation xi plus variance of w, okay, and variance of summation xi is nothing but n times sigma square, and this is whatever has been given to you, which is 40 turns. Okay. So, this is 40 standard deviation. So, 40 square. Okay. So, this is n into 0.3 square plus 40 square equal to 0.09 n plus 1600. Okay. So, variance is this. Okay. So, y, which is defined as the difference between the net weight from the cars on the bridge to the weight that can be withstood, is this. So, y is a random variable, okay, which has a mean of 3n minus 400 and a variance of 0.09 plus 1600. Okay. So, we have been asked to calculate, okay, probability summation xi minus w greater or equal to 0. Why? Because if summation xi is less than w, there is no damage on the bridge. Okay. Only when summation xi begins to exceed w is there any chance of the bridge. Okay. So, we have been asked to calculate this is roughly equal to 0.1. Okay. So, probability of summation xi minus w, this can be written as probability of z or summation xi minus of 3n minus 400. Okay. So, this is the net mean minus root of 0.09 n plus 1600, because the variance was 0.09 n plus 1600, okay, is greater or equal to 0. Okay. P of z of greater or equal to 0. So, P of this is basically greater or equal to 0 minus of 300 minus 400 by root of 0.09 n plus 1600. Okay. And this we are given approximately equal to 0.1. So, probability of z greater or equal to minus of 3n minus 400, okay, by root of 0.09 n plus 1600 is equal to 0.1. So, if you look up the table, this is roughly P of z greater or equal to 1.28. So, this would mean that 400 minus 3n, okay, by root of 0.09 n plus 1600 is less or equal to 1.28. Okay. And from here you can find out the value of n. So, this is one equation, you take a square and determine the value of n. So, this n will be order 117. Okay. So, this allows that if there are roughly 120 cards, then there is a chance that there is a 10% chance that the bridge will get damaged. Okay. So, here we made use of central limit theorem, but we first defined our random variable y as the difference between the total weight of the cards on the bridge minus the weight that could be withstood, because we are calculating the chance of damage. Okay. Now, so imagine your x, so xi's are binomial random variables. Okay. X can be of any distribution, x can follow any distribution. Okay. Let us assume that xi's are binomial random variables. Then we know that E of xi, okay. So, we can call xi, okay, 1 if ith trial is successful, okay, equal to 0 otherwise. So, we have previously demonstrated that E of xi is p and variance of xi is equal to pq. Okay. So, if we define a random variable x, which is summation of xi, okay. So, in that case, again by invoking central limit theorem, I can say summation xi minus, so this is, so x is summation of xi. So, summation xi will have a mean of np and a variance of npq. Okay. So, npq is going to be the variance of this x and np is going to be the mean of this x. So, this means that summation xi minus np by root of npq is a standard normal variable. Okay. So, one thing is there is a requirement on the value of n depending on what distribution these x's follow. Okay. So, generally if xi's, so if xi's are themselves normal variables, normal random variables, then for any n, summation xi is going to be normal. Okay. But if xi's are non-normal, okay, and maybe even biased, in that case you need to have n greater or equal to 30 for this distribution to be a normal distribution. Okay. So, for a binomial random variable, Okay, we have summation xi follows normal with mean of NP and variance of NPQ. Okay. So, I will conclude my lecture today by saying that we can briefly remember about central limit theorem and how we can use central limit theorem to estimate certain things given the sample distribution. Okay. So, as we saw that summation xi will follow a normal distribution with mean of n times mu and variance of sigma square n, which means the standard deviation will be sigma root of n. Okay. And depending on the type of distributions. So, if your underlying xi's are themselves normal random variables or even symmetric, okay, then for any or small values of n, 2 or 3, you will have summation xi or summation xi by n follow normal distribution. Okay. But if xi's are non-normal in nature, particularly if they are an asymmetric, then you need n greater or equal to 30. With that, I conclude my lecture today. I look forward to meet you again in next class.